Okay, for this first question, we're asked to look at the attraction between a carbon atom and a chlorine atom in a molecule of tetrachloromethane. So what we want to first think about is what type of bonding do we have here? Are we talking about intermolecular bonding, which is the different bonds between different molecules, or are we talking about intramolecular, which is the bonds within a molecule? So we're asked about the carbon atom and the chlorine atom's attraction. So we're talking about within the molecule here. So if I draw a diagram of tetrachloromethane, what we're asked is what type of attraction is responsible for holding the carbon to the chlorine atom, basically. So this bond here, for example, but there are 4 of those bonds, so you could choose any of them. Well, it's not going to be intermolecular, so we can get rid of hydrogen bonds and London dispersion forces. What we're left with is polar or non-polar. And to determine what is polar and what is non-polar in terms of a bond, we need to look at the electronegativity of each of those atoms. So carbon is 2.5, chlorine is 3, the chlorine atom will have a partial negative charge and the carbon atom will have a partial positive charge, so we end up with a polar bond. So the answer here is polar covalent. Okay. So in this example, we're asked what type of bond holds together the 2 chlorine atoms in a molecule of chlorine. So something like that. Well, what we have here is a diatomic element. We've got 2 of the same atoms held together by a covalent bond, so we can again eliminate hydrogen bonds and London dispersion forces because we're talking about the bond that is within a molecule, not between different molecules. So the last thing I have to think about is whether it's polar or non-polar, and anytime you have the same atom bonded to each other, then it's going to be non-polar because the electronegativities are the same, 3 and 3, which means those electrons are shared equally in the middle. Okay, so in this question we're looking at the force of attraction between a hydrogen atom and an oxygen atom in a molecule of water. So water, H2O, has this bent or angular shape, and we're looking at the bond between the oxygen and the hydrogen atom. So the oxygen atom has an electronegativity of 3.5, where hydrogen has an electronegativity of 2.2. So what that means is the oxygen atom is going to have a stronger attraction for the bonding electrons than the hydrogen, so the electrons will not be shared equally, and the oxygen atom will have a greater share of those electrons, giving it a partial negative charge and the hydrogen a partial positive charge. So that bond that's holding together the oxygen and the hydrogen atom is a polar covalent bond. Again, we can neglect hydrogen bonds and London dispersion forces because we're talking about the bonds within a molecule, not between molecules. So for question 4, we're looking at the force of attraction between 2 adjacent pentene molecules. So this is the first question where we're looking at bonds between different molecules as opposed to within the one molecule. So we can immediately get rid of the first 2. Non-polar covalent and polar covalent bonds hold atoms in a molecule together. There are no polar or non-polar bonds between different molecules. That's not where they're found. So what we're left with is hydrogen bonds and London dispersion forces. Hydrogen bonds occur between different molecules which contain NH, OH or FH groups. Well, we can see this molecule here doesn't contain an NH, an OH or an FH group, so by default it can't be hydrogen bonding, which leaves us with London dispersion forces. For question 5, we're looking at the attraction between the carbon atom and the oxygen atom within a molecule of carbon dioxide. So a carbon dioxide molecule here, and we're looking at this bond here between the carbon and the oxygen atom. So a carbon atom has an electronegativity of 2.5, oxygen atom has an electronegativity of 3.5. So as a result, the electrons are not shared equally within this covalent bond, and the oxygen atom has a greater attraction for those electrons, giving it a partial negative charge, and the carbon a partial positive charge. So if we look at our options there, it's not going to be hydrogen bonds or London dispersion forces because they are intermolecular or van der Waals forces. And we've established that we have a polar bond because there is a dipole across the bond, so that gives us polar covalent bonds. Question 6, the attraction between two adjacent molecules of hydrogen fluoride. So hydrogen fluoride diatomic molecule. Hydrogen's got an electronegativity of 2.2 and fluorine's got an electronegativity of 4. So fluorine, the most electronegative element. And as a result, what that means is quite a strong dipole was formed with quite a strongly partial positive and partial negative charge being induced. So the fluorine is quite strongly partially negative, and as a result what we end up with is strong attractions between the partial negative side of one molecule and the partial positive side of another molecule. So this attraction here between the opposite charges of opposite molecules, or for different molecules, and that bonding there is known as hydrogen bonding. As a reminder, hydrogen bonding occurs between different molecules which contain NH, OH or FH groups. And in this case, we have an FH group. So the answer here is hydrogen bonds. So question 7 is actually quite a tricky one. It's asking you about polypropene, which is a molecule you've probably not really encountered before. Polypropene is a polymer, and polymers you covered back in National 5, and this might have been an example you saw in National 5, but polymers was such a brief topic in National 5, maybe 2 or 3 lessons, that it's quite easy to be overlooked. So if you found this question tricky, then that's okay. What a polymer is when many monomers join together. A monomer is a small molecule often containing a double bond, and if many of those monomers link together in a linear arrangement, you end up with a polymer. So the way that that happens is the double bond in the monomers breaks, and those covalent bonds that have been freed up essentially are able to bond to adjacent monomers. So we can see here that bonds have been formed here, 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 and out the sides, and the double bond has been broken. So essentially we've formed a polymer. So it's a linear covalent structure. So already I'm leaning towards option D. And it says linked by van der Waals forces. So that can be maybe a little bit misleading in what it's meaning, because the monomers are joined together by covalent bonds, but the linear covalent structures are linked to other covalent structures by van der Waals forces. So what I've got here is one polypropene chain and another polypropene chain, and between these polypropene chains there are going to be van der Waals forces, and there's actually going to be London dispersion forces occurring. London dispersion forces occur between all atoms and molecules, and it's due to the random distribution of electrons within the atoms or molecule. So it's not a 3D ionic lattice, it's not a 3D covalent network, it's not a 3D structure linked by hydrogen bonds because we've got no OH, NH or FH groups. It's simply a linear covalent structure which is linked to other linear structures by van der Waals forces. Quite a tricky one, don't worry if you got that one wrong. So in question 8 we have magnesium chloride, MgCl2. If you're unaware of how to work out the formula for that, you could use SbSdF. This one, quite a relatively straightforward one, because what you have is a metal and a non-metal. So if you use your National 5 knowledge, you're able to pretty quickly decipher that this is an ionic structure. We've got a metal and a non-metal. But you could also look at the difference in electronegativity, and what you'll find is quite a large difference. So we are pretty confident that this is ionic. And if it's ionic, then it must be an ionic lattice. It's not going to be covalently bonded in any way, and ionic structures can't form molecules, obviously, and if they can't form molecules, they can't have hydrogen bonds. So once you have determined this is ionic, there's only one option, and that's ionic lattice. Silicon dioxide is a covalent network. Silicon is an element that exists naturally as a covalent network, but it can also form covalent networks by bonding to other atoms, such as oxygen to make silicon dioxide, or carbon to make silicon carbide. So we can see here the structure of silicon dioxide. We can see it's that classic covalent network structure. And once we have determined it's a covalent network, we just go to the options. Any mention of ionic we can get rid of because it's covalent. Any mention of molecules we can get rid of because it's a network, it's not made of molecules. And any mention of van der Waals forces we can get rid of because in a covalent network the only forces of attraction between different atoms is covalent bonds. That's what makes covalent networks so strong, because to melt, to boil a covalent network, you need to break strong covalent bonds. So there are no intermolecular forces, there are no van der Waals forces. So it can't be option D, so it's going to be option B, covalent network 3D structure. So ammonia is NH3. It's got a pyramidal structure, which is 1 nitrogen at the top and 3 hydrogens forming the base of this pyramid. So nitrogen's got an electronegativity of 3 and hydrogen's got an electronegativity of 2.2. So as a result, we end up with a strong dipole being formed with the nitrogen being partial negative and the hydrogens being partial positive. So if we've got two adjacent or nearby ammonia molecules, so if I draw another one down here, and I show the same dipole being formed because it is a permanent dipole, so the same dipole being formed, so the nitrogen is partially negative and the hydrogen is again going to be partially positive. Between these ammonia molecules, between the partial negative nitrogen of one molecule and the partial positive hydrogen of another molecule, there will be forces of attraction because positive is attracted to negative, and this attraction here is called hydrogen bonding. Remember, hydrogen bonding occurs between NH groups, OH groups, or FH groups, and here we have NH groups. So it's not a 3D ionic lattice, it's not a 3D covalent network, it's not a linear structure, it's 3D molecules. We know it's 3D because we can see that this bond here is coming towards us and this bond here is going away from us. So we know it's a 3-dimensional molecule and it's linked by hydrogen bonding. So what kind of attraction occurs between two adjacent ethanol molecules? So I've got two ethanol molecules here, and what's important to first note is that ethanol molecules contain an OH group, which is quite a strongly polar group. So the oxygen has an electronegativity of 3.5 and hydrogen has an electronegativity of 2.2, which results in the oxygen atom being quite strongly partially negative and the hydrogen being quite strongly partially positive, so you get quite a strong dipole being formed, and we can show the same in the other molecule. So if we've got two adjacent ethanol molecules with these strongly polar groups, then the oxygen atom of one molecule is going to be attracted to the hydrogen atom of another molecule because the oxygen is negative and the hydrogen is positive and opposites attract. So we'll end up with an attraction forming between the O of one molecule and the H of another molecule, and this attraction here is known as hydrogen bonding. As we saw in the last slide, hydrogen bonding occurs between NH, FH and OH groups. So the answer here is hydrogen bonds. So potassium fluoride, we have KF. Potassium has an electronegativity of 0.8, fluorine has an electronegativity of 4, so that's a pretty significantly large difference in electronegativity. Plus we have a metal and a non-metal, so all the signs here are pointing to ionic. So as mentioned back in question 9, silicon exists naturally as a covalent network. Alongside boron and carbon, it is one of 3 elements in the first 20 that exist naturally as a covalent network. So to melt a covalent network, you need to break strong covalent bonds. There are no van der Waals forces in covalent networks, no LDFs, no permanent dipole, no hydrogen bonding. The only type of bonds that are present in a covalent network are covalent bonds. So to melt a covalent network, you need to break covalent bonds. Okay, we're talking about ice here, and ice is H2O, water. So if I draw a few water molecules, I arrange them like this. And the reason I'm arranging them like this is because that's how water molecules are arranged in ice, and it's that crystalline structure in ice. So what we have here in a water molecule is obviously a polar molecule, with the oxygen being partially negative and the hydrogen being partially positive. So when we take ice and we melt it, what's happening is the water molecules are being moved further apart, and they're moved further apart because the intermolecular bonds between water molecules are being broken. Covalent bonds aren't being broken. Water molecules stay intact, whether they're in ice, whether they're in water vapour, or whether they're in liquid water. What is being broken is the intermolecular forces, and specifically it's hydrogen bonding, because between the O and the H here we have a force of attraction known as hydrogen bonding. Remember, hydrogen bond occurs between NH, OH and FH, and here we have OH, so it's going to be hydrogen bonding. So this is quite a similar question to the one we just did. We have hydrogen fluoride this time. I'll draw two molecules of hydrogen fluoride. Hydrogen fluoride is a strongly polar molecule because we have hydrogen, which is an electronegativity of 2.2, bonded to fluorine, which is the most electronegative element with electronegativity of 4. So as a result, that gives us a partial positive charge on the hydrogen, a partial negative charge on the fluorine. I'll show that in the other molecule as well. So anytime we melt a covalent molecular substance, what is being broken is the intermolecular forces between molecules. We don't break the covalent bonds when we melt or boil a substance. The covalent bonds stay intact. So this bond here, that bond does not break, and that's a common misconception that hopefully by higher has kind of been drilled out of you, but the covalent bond does not break. What does break is the force of attraction between the partial negative atom of one molecule and the partial positive atom of another molecule. So this bond here is between a H and an F. That fits the criteria for hydrogen bonding. So question 16 is quite a controversial one because the answer scheme is actually incorrect. What we have is sulfur trioxide. So sulfur trioxide, I wouldn't expect you to really know the structure of. This is one that you maybe have to go on and look at online. Sulfur trioxide contains one sulfur atom and 3 oxygen atoms, with the oxygen atoms being double bonded and surrounding the sulfur on all sides. So if we look at the electronegativity, sulfur has an electronegativity of 2.5 and oxygen has an electronegativity of 3.5. So we can see here that yes, the sulfur to oxygen bond would be polar because there is a difference in electronegativity. However, what that will give us as a result is a partial negative charge on all of our outwards facing atoms. So the whole outside of the molecule will have the same charge. So what that tends to indicate is that you have a non-polar molecule. For a molecule to be polar, you need a separation of charge for one end of the molecule to have one charge, positive or negative, and the other end of the molecule to have the opposite charge. But what we have here is the same charge on all sides of the molecule, so that is giving us a non-polar molecule. Oops. So if it's non-polar, then it's not able to form permanent dipole to permanent dipole interactions. So this is actually incorrect. The only type of interaction that can occur between non-polar molecules is London dispersion forces. So hydrogen sulfide has the formula H2S. It's got a very similar structure to H2O actually. So we're just going to replace the O in H2O with an S. So we still have that angular or bent shape. So if I draw two hydrogen sulfide molecules, When we melt hydrogen sulfide, as I've said previously, we're not breaking covalent bonds. So any mention of covalent bonds we can get rid of. It's non-metals, so it's not going to be ionic bonds. And we don't have an NH, OH or FH group, so it's not going to be hydrogen bonds either. So we're left with London dispersion forces of permanent dipole to permanent dipole. And the way that we determine what the answer is we look at whether we have polar molecules, which would give us permanent dipole to permanent dipole, or we have non-polar molecules, which would give us London dispersion forces. So let's look at the electronegativity. Hydrogen is 2.2, sulfur is 2.5. So as a result, the sulfur atom is going to be slightly partially negative. It's not a huge dipole being formed, but there is a difference in electronegativity, so there is a slight separation of charge. Not a large separation of charge, but still the electrons are not even shared completely equally. So slight dipole being formed in the molecules, which as a result is going to give us permanent dipole to permanent dipole interaction between the partial negative sulfur and the partial positive hydrogen of different molecules. Oops. Question 18, we have carbon monoxide, which is just one carbon atom bonded to one oxygen atom. We have a triple bond. You've maybe not seen this molecule before, so this is maybe one you had to look for online on Google. But what we have here is a carbon bonded to an oxygen, essentially. The carbon's got an electronegativity of 2.5 and oxygen's got an electronegativity of 3.5, which means the carbon atom is going to be partially positive and the oxygen atom partially negative. So the interaction between carbon monoxide molecules, different carbon monoxide molecules, is going to be a permanent dipole to permanent dipole interaction. We have a permanent dipole within the molecule, so it can't be London dispersion forces only, because we've got a little bit of a stronger interaction than that. Ionic bonds are present in ionic compounds. We have a covalent molecule. Covalent bonds are not broken during melting unless you have a covalent network. And we don't have any OH, NH or FH groups, so it can't be hydrogen bonding. So the answer is permanent dipole to permanent dipole. Question 19, rubidium chloride, RbCl. You probably won't have heard of rubidium chloride before, but you don't need to have heard of it to be able to work this out, because we know that rubidium is an alkali metal, group 1 metal, very low electronegativity. Chlorine is a non-metal, it's quite a high electronegativity, and when you've got a significant difference in electronegativity values, specifically between a metal and a non-metal, what you end up with is ionic bonding. So to melt an ionic compound, you need to break ionic bonds, the force of attraction between positive and negative ions. So we have ionic bonds here. It's not covalent bonds because we have an ionic compound. Covalent bond exists between two non-metals. Hydrogen bonds exist between covalent molecules. London dispersion forces occur between different atoms or molecules. We have one large ionic structure, so there's no LDFs in there, and the same explanation for PD to PD. Okay, question 20, we have butane. So we have a 4-carbon chain, and it says ane at the end of the name, which tells us that it's an alkane, which means it contains all single bonds. So we've got to have 10 hydrogen atoms surrounding this 4-carbon chain. The electronegativity of hydrogen is 2.2. and carbon is 2.5, so quite similar in electronegativity, but not identical, so we've got a slight dipole being formed. So the hydrogen is less electronegative than the carbons, so the carbon will have a partial positive, and the hydrogen will have a partial positive, and the carbon will have a partial negative. And if we draw all of those partial positive charges on the hydrogen surrounding the chain, you'll find that you have the same charge at all sides of the molecule. And when you have the same charge, you have a non-polar molecule. For a molecule to be polar, you need a separation of charge, or charge split across the molecule. So one side positive, one side negative. If the whole outside of the molecule is positive, then what you have is the same charge present everywhere in the molecule on the outside, so it's a non-polar molecule. Once you've established that the molecule is non-polar, and that the dipoles have cancelled out, we can eliminate some of the answers. It's not going to be ionic, of course. It's not going to be covalent because we don't break covalent bonds when you melt a covalent substance. It's not hydrogen bonds because we don't have OH, NH or FH groups, and it's not permanent dipole to permanent dipole because that only exists between polar molecules, and we have a non-polar molecule, so it's London dispersion forces. Question 21 is boron. Boron is a large covalent network structure. It's got a really complicated covalent network structure that you're not expected to know off by heart in higher, but what you are expected to know is that it is a covalent network, and the covalent networks have high melting and boiling points because to break them up you need to break strong covalent bonds. So when you're melting boron you need to break covalent bonds. There are no ionic bonds in boron. It's an element, therefore not a compound. It's not got any hydrogen bonds because hydrogen bonds exist between different molecules. We just have one large network, and the same logic for London dispersion forces and permanent dipole to permanent dipole. There's actually another wee error in this question here in the marking scheme. It says the answer is covalent bonds, whereas that is not the correct answer. Phosphorus is a covalent molecule. It's formed between 4 phosphorus atoms. It's formed this tetrahedral arrangement, this 3D structure. To melt any covalent molecules, you never break covalent bonds. What you break is the intermolecular bonds between different molecules. So if we wanted to melt phosphorus, we are not breaking these bonds here. We're not breaking the bonds that hold the phosphorus atoms together. We are going to break the bonds between this phosphorus molecule and another phosphorus molecule. And if it's a non-polar molecule, as all elements are, you're going to have LDFs. Because permanent dipole to permanent dipole only occurs between polar molecules. Hydrogen bonds only occur between polar molecules with NH, OH or FH groups. And ionic bonds occur in ionic compounds, and we're just talking about an element here. Question 23, we're looking at the strength of bonds. The correct answer is D here, because London dispersion forces and hydrogen bonding are both types of intermolecular bonds, with London dispersion forces being the weakest type of intermolecular bonds and hydrogen bonds being the strongest type of intermolecular bonds. Remember, intermolecular bonds occur between different molecules. It's not within a molecule, but it's between different molecules. So those are our intermolecular bonds, LDF first, and then hydrogen bonding because it's stronger, but it's not as strong as covalent bonds. Covalent bonds are much stronger. They hold atoms together in a molecule. To break them, you need to input a huge amount of energy, as seen in covalent networks. So these are called intramolecular. Okay, so intermolecular bonds are weaker than covalent or ionic bonds. Graphite is a covalent network structure, but as opposed to diamond, which is a three-dimensional structure, in graphite what you have is sheets of covalent networks. So they move along as kind of planes, and between these sheets of covalent networks you have London dispersion forces. So between two sheets of graphite in your pencil you have London dispersion forces, and as you write with the pencil, or you stab the pencil against the desk, the graphite is obviously going to crumble, because all you're doing is you're breaking the London dispersion forces between the different layers of graphite. You're not breaking the covalent bonds within the network. What you're doing is you're just shaving off different layers of the graphite structure by breaking the LDFs. Okay. Then, last but not least, the three types of van der Waals forces, sometimes called intermolecular forces. They are the forces that exist between different atoms or molecules, and they are permanent dipole to permanent dipole, London dispersion forces, and hydrogen. And the only answer there that fits those three is option B. Okay. Thanks for watching, guys. Hopefully this has been helpful for you, and if you need any more feedback or you get any questions, please just let me know.